Hello and welcome to the online version of Fun with Spreadsheets. This session is a STEM session aimed at teachers in schools and teaching science and mathematics in a way using spreadsheets. It's undoubtedly a fairly nerdy session, and if this description doesn't fit you, I'm slightly surprised you're here, but welcome anyway. It's good that you're here. At the outset, I want to acknowledge Matt Parker, who inspired and supplied some of the material for this session. Matt has described himself as a stand-up mathematician, and I encourage you to look for him on YouTube and other places later on. Today, I'm going to show you my favorite spreadsheet. It is a doozy, and although you doubt it even now, in 4 minutes, you are going to agree with me that this spreadsheet is cute and you're going to want to make one too. After that, we turn to the dark side, when spreadsheets go wrong. And then we talk about how we can use them as a tool in various kinds of teaching science, biology, and maths. But before we get to go to cute, we have to have a quick history lesson. Most people think spreadsheets are only for work, and indeed they have a proud history of work, and I think they're the greatest tool ever developed for handling two-dimensional data. But they also have a long and proud history in recreation. The first modern computerized spreadsheets were created by these two guys, Dan Bricklin and Bob Frankston. Here they are, the two men who created the world's first computerized spreadsheet. And they were pretty proud of it too. Their spreadsheet was called VisiCalc. And yes, they created their spreadsheet for work, but I don't know, you can look at those guys and I'm pretty sure they use spreadsheets recreationally as well. VisiCalc was their first spreadsheet, and they created it for the Apple IIe, which anyone over 40 might recognize from their days in school. They tried, but failed, to make it work on the base level of the Apple IIe. In fact, if you wanted to run VisiCalc, you had to buy the higher spec Apple IIe, which had 32 kilobytes of memory. Now, this spurred sales for the more expensive computer and greatly contributed to Apple's early rise in the computing world. However, while VisiCalc is often thought of as being the first spreadsheet, it wasn't. That honor goes to this. This is a parchment from about 2500 BC, and it's actually also the earliest writing on paper or papyrus. And that is what I think is the world's earliest spreadsheet. Now, so we turn now from here to my favorite spreadsheet. Now, here it is. This is my favorite spreadsheet. I've got rows of numbers and columns of numbers. Highest number is about 255. Lowest number is about 0. And it goes quite a long way. I think there's 96 rows and there's 384 rows and there's 96 columns. So you can see there's a lot of numbers there. And this is a really good spreadsheet. And the reason I like it is you can do this. You go to a cell and over in the Home tab here, you've got conditional formatting. And go, yeah, let's do conditional formatting. Let's make a new rule. And we're going to go from a number of 0 up to a highest number of 255. And to 0, we'll say black. And 255, we'll say white. Go, okay. And now that cell is conditionally formatted, which means the format depends on what is in the cell. So there's 49. If I put 10, it gets a bit darker. If I put 100, it goes to a shade of gray. If I go 200, it's a light shade of gray. If I go 255, perfect white. Okay, and that was probably around 55, I think, so I'll put it back to there. Now we're going to go and copy this to the whole spreadsheet. So I'll format Painter, and then I'll highlight everything, and that has applied that conditional formatting to everything in that spreadsheet. And you can see there's now blotches of black, there's blotches of gray and white. And hopefully some of you can already see where this is going. So what I'm going to do is zoom out a little bit. And if I keep zooming out, we'll eventually see that these blotches start to make sense. And they form a photograph. And that photograph, of course, is me at the age I was when I first discovered the joys of spreadsheets. What this is showing is that every spreadsheet, every picture, every digital picture is just a spreadsheet of numbers and the conditional formatting. So every one of those cells has a number in it, and every one of those numbers corresponds to a shade of gray. So zoom back in again. There's a dark spot, that's got 76. Here's a light one, 203. That is a photograph. And of course, we can take it to the next level. So I'll go to my second favorite spreadsheet now. This is my second favorite spreadsheet. And again, you'll see a similarity. There's just rows of numbers from low of about 0 to a high of no more than 255. But this time, we've been a little bit more clever with the formatting. In this one, I've got rows of alternating red and green and blue, red, green and blue. And if you come down to here, you'll see that the formatting, let's have a look at this one here. If I go have a look at the formatting on this one, and I go to Manage Rules and Edit Rule, you can see that it goes from 0 in black, 255 in bright green. Or I have a look at one of the red ones, is a similar thing. Zero is black, highest one is 255 in the bright red, and you'll find the same in the bright blue. And so I can play with these numbers as well. There's 191. Let's change that down to 50, and you'll see that that goes to a very dark green. If I change it down to 0, it's completely black. Or if I change it to 255, you'll see the brightest green that this screen is able to show. And let's put it back to somewhere around 193, I think. And again, already some of you can see where this is going. When I zoom out, I get another image start to emerge, and this time the image is in color. Because color screens are made up of a combination of red and green and blue pixels. In fact, every digital photograph, every color digital photograph is just rows of these alternating color pixels. And I'll show you that in a second. But that is a color photograph. In fact, if you take a BMP file, bitmap file, you throw away some of the coding at the beginning, which sets it up, and some at the end, you'll just find strings of numbers with commas in between, which are those numbers in the spreadsheet there. And that's what every digital image is. It's a spreadsheet. In fact, when you go to the movies, it's spreadsheet after spreadsheet thrown at you. 24 times a second, the average movie, you see about 170,000 spreadsheets. I don't know if that should make you excited. It makes me excited. Now, there are some other things. This is what I've talked about, a bitmap, a BMP file. Most images these days are in a different format, often called JPEG. And JPEG is a similar idea, except a little bit more complicated. What they've done in JPEG is say, you know what? The pixels around this one, there's 214. The pixels on either side are actually pretty close to that. There's 212, there's 213. And so it's not like a radically different number. And so they said, all right, instead of saying, let's just pick a whole new number, let's put a gradient there and say from here to here, we get a gradient of color decreasing or increasing that way. And a gradient of color increasing or decreasing. So if you go down, see 213, 213, 216, you can see it doesn't change much. And by having a look at the data in that sort of format, they're able to actually compress the data. And instead of a bitmap taking a couple of megabytes, you can squeeze it into several kilobytes. An MPEG, which is the motion picture version, is the movie version of the similar thing. It's compressing data and selectively throwing it away without us noticing. But fundamentally, when it comes back to displaying it and displaying it on a screen, every single image is just those alternating rows of red, green, blue, like a spreadsheet. I'll prove it. I'll take my phone here, turn on the selfie camera, and you can see me and the camera, and we're going to take a picture. Okay? And there's the picture we've got. And I've got here a USB microscope. The other end of this cord just plugs into the camera, and it behaves just like a webcam. And you can pick these up for about between $25 and $50 or a bit more. So not too expensive. But I put this microscope on the screen of the phone there, and the image is being shown up on the screen here. And you can see if I focus it and hold it still enough, that the whole thing is just rows, there we go, rows of red, green, and blue, just like a spreadsheet we had before. That's the white section. If I take it down and put it on the blue shirt, you can see that the rows of blue cells are much more intense and the other colors are much darker. So it's just the varying intensities of red, green, and blue on my phone screen. Now, a little word of warning. If you're going to do this, just check the phone first. because I once disproved this by picking up an audience member's phone, and their phone screen wasn't set up like that. There are some phones which have a polar or a radial pattern, so the colors are not laid out like a nice spreadsheet. The principle is the same though. It's just every image is made up of that red, green, and blue in varying intensity. From here, the discussion can move fairly easily into biology and talking about the makeup of our eyes. As you know, of course, our eye cells have cones and rods in them. And the cones, we've got 3 different types of cones in our eyes. One is sensitive to red, one sensitive to green, one sensitive to blue. And that's the reason why, although each color is made up of an individual wavelength, almost any visible color can be mimicked by varying shades of red, green, and blue. And that mirrors what's going on in our eyes. However, there are limitations to our technology versus biology. Now, just like our eyes, where we have the red and the green and the blue cones, the technology we have mimics that in a way, but there are limitations. If we make a graph of all the colors visible to humans, we can show it in a shape like this, where the violet is down this end and the ultraviolet's over here. The red and the infrared is just outside there, and we've got through the middle of the greens. And that represents all the colors that humans can see. Now, to show that on a screen, we pick 3 points within that zone, and we can mimic all the colors between them. So, for example, if we pick a blue light, a red, and a green, which is what we did in our spreadsheet, it forms a triangle, and any color that lies within that triangle can be represented on the screen. Now, in theory, you can pick any 3 colors, but the colors you pick, only what lies inside that triangle are capable of being shown on the screen. So you have to pick your colors carefully. You, of course, have to get them inside that line, because if they lie outside the line, then the colors aren't visible to humans, so you won't see anything at all. And you can see from this triangle that there's a lot of color that people can see that's actually missing, especially up in this green zone here. That's right. A lot of colors in nature, especially in the green spectrum, can't be shown accurately on TVs or on screens because they fall outside that triangle. In fact, even the green here, you aren't seeing what I'm seeing here because of the limitations in the camera and the limitations of your screen. So all I can say is, imagine the green is a bit like that, but it's not the same. This also works for a 3-color printing process. You can't print the sort of colors that lie outside the triangle. So there are some colors in nature you just can't see in a photograph or a book. So all those colors are missing. Now, of course, you can make a larger triangle. You simply select your lights more carefully, and then you'll be able to show more colors. But even here, if you can see from the shape of it, that even with the best triangle, there's always going to be colors missing. And indeed, there are lots of standards for showing colors. Here are just some of the standards that you can see. We've got visible spectrum, a wide gamut. There's all these different standards, each of which have their own peculiarities and their own disadvantages and advantages. But whichever one you see, there's going to be colors missing. But getting back to our spreadsheet and how the class might react to something like this, you can then lead them into a discussion, I think, about the difference between data, which is the individual numbers you see on the screen here. Each of these data points is a real legitimate data point, but they don't actually tell you anything. So the difference between data and information, which is what that data point represents, it represents a color. And then the difference between information, which is those colors, and information and knowledge. And the knowledge, of course, is that all those data points form a picture, and it's a picture of something. That's the knowledge. And then if you want to go further, you could even say the difference between knowledge and wisdom. Knowledge is that photograph. Wisdom is me knowing that I probably should have picked a different photograph. Now, to go back to an earlier point, there may have been some of you wondering about the range 0 to 255. Why did I pick that? Honestly, I could have picked any range from 0 to 10 or 0 to a million or whatever. But we did pick 256 because that mirrors how computers work. The majority of computing is done with 8-bit numbers. That is 8 binary digits. Binary digits, of course, are 1 and 0. I'm sure you're all familiar with counting in binary. With 8 digits, the largest number that can be held is 256, which is why we go from 0 to 255. And you get to that by taking 2 and taking it to the power of 8. Now, this number shows up a lot in computing. In Minecraft, the maximum height of the world is 256 units tall. If you go build a tower in Minecraft, when you get to 256, you can't go any more. If you dig a hole, you can only go down 256 units. In WhatsApp, you can have a maximum of 256 people in a group. This number comes up over and over and again in computers. Now, by definition, there are 8 bits in a byte, but that wasn't always the case. In fact, IBM made that definition. The 8 bits through a byte system was pioneered by IBM. And there were several competing computing systems. There was 4-bit, there was 6-bit, there were 7-bit systems as well. 8-bit allowed IBM to be backward compatible with all the previous programming, all the way back to their punch cards. And that system carried through. So what went along with that, all the way back to their punch cards, and also didn't take up too much space, because that allocated a bit of memory, and if all the numbers were quite small, that would be wasteful in computing space. So when looking at 8-bit images, you get to multiply the 256 for the green, the red, and the blue by each other, so that when you multiply them together, you get 16,777,216 possible number combinations, which are also possible colors. And those are the possible colors that TVs and monitors can display. And this is normally rounded down to 16 million. Our eyes can distinguish about 10 million colors, so it's not a bad match for a fluke. Now, getting back to our spreadsheet, I've got to admit, entering all those numbers was pretty boring, even for me, even for a guy like Matt Parker. So, thankfully, he automated it, which I'll step you through now. A couple of minutes ago, I took a picture on this camera. And so we're going to turn that into a spreadsheet. So we open up Google or Google Chrome or any browser and type in think-maths.co.uk/spreadsheet. Or if you go thinkmaths.co.uk and you'll see a link to spreadsheet. And you'll see over here, it says upload a photo, and then you can download it as a spreadsheet. So if I choose a file, I go here, this one's labeled 1 to make it nice and easy to find, and I go open, and then press convert to spreadsheet. And it'll immediately download it as a spreadsheet. There it is there, and I go open. And it'll open up Excel. It may throw up a warning message or two, so click past them, that's okay. And then, that is the photograph. So I'll enable editing here, and if I zoom out, there it is. So if anybody asks you for a photograph and you don't really want to comply, you can send them a spreadsheet instead. So let's say you got your class together to do this. They each make a photograph of themselves, and all these photographs will come out the same size. They're not very high resolution. So then we can say to the class, all right, what are some of the things we can do with this? Let's go zoom back in again and come to the bottom. And let's say who in the class has got the highest sum? If you add up all the numbers, okay? So I'll zoom in here and I'll go equals sum. I'll make that a bit bigger. So equals sum, and then we open bracket, and then we have to go from the first cell to the last cell. The first cell is A1, because that's always the top left-hand corner, then a colon, and I just happen to know that in this case, it's always DX 216, and that will get you the sum of all those numbers. And in this case, it's 3,283,397. What if you want to know what the average of my face is? I've always wanted to know what the average of my face is. So go AVG for average, A1 colon DX216. And the average of my face is 118.75. Well, that's fine. So then you could put to your class and say, all right, if you wanted to make either a high number or a very high average, what sort of photograph would you take? And you can talk the students through whether they'd take a photograph which is very light or very dark, or what sort of colors they'd have involved to get those averages. Then you could talk to the students about maybe they can manipulate the pictures just by changing the numbers. So here I've got my face here. I've got some eyes here. So let's brighten my eyes up a little bit. Put 200 in there, 200 there, 200 there. That's going to put a nice white speck in both of my eyes. And you can get your more persistent students perhaps starting to draw on themselves. Maybe they're going to put white eyebrows on or black or something like that. And we'll zoom out there and you'll be able to see two lovely white specks in my eyes. Oh, that doesn't look evil at all. Oh boy. So you can get your students doing manipulations of things like that. You can also pose a picture. All right, the question, how would you make a negative of that? There's a couple of ways. Now, if I go back to the black and white picture, it was fairly easy. There's my favorite spreadsheet, and there's the black and white version. All I have to do here in the black and white version is swap these two conditional formats around. So I go Manage Rules and Edit Rule, and instead of making the 0 black, let's make the 0 white, and let's make the 255 black. Go OK, and that will turn that into a negative. By the way, this picture here started off as a color picture, and I took out all the color formatting and I highlighted the whole thing as just black and white. And the reason I did that is because in this color version here, if you go to edit all the rules, you'll find you have to do each line individually. So it's quite a lengthy process. So if you want to turn this into a negative then, what I suggest you could do is maybe over here, where you got some blank space, make a whole field of 255s there on the screen, the same size as the picture. And then if you copy and paste over there, and instead of just doing a paste, do a paste where you do an operation on it. So you go 255, subtract whatever that value is, then you'll get the image, the real image there, the real image here on the screen, and the negative image over here. So you can have your students do that. And by doing this, you're helping the students manipulate large amounts of data. I mean, one way they could do it is go down and physically change every number. But one of the things you want to teach them is you've got a million numbers here you've got to deal with. How are you actually going to deal with that? If you have quite senior students now, maybe high-level maths, fluent maths or something, and you think of these things as coordinates, X, Y, and Z coordinates, then each of these set of three cells represents a point in space in coordinates. And where this goes from here in the red, green, and blue axis is you can then rotate those axes around and then start playing with the colors here. And where that has real application in life is in automating video recognition and picture recognition. So for example, when you have you're looking for a lost airplane, the MH273, I forgot what number it was, out at sea, and you can automate a lot of that footage and look for the parts of the airplane because you know that most of the sea is blue. And everything that is not blue is something that's worth looking at. And so you rotate these rounds so that everything is either blue or not blue. And then you have a program which then looks at these numbers and says, all right, what numbers are blue and therefore I can ignore, and what numbers are things that are not blue. And then the computer program will pull out those images and say, you know what, here's a bit of that video footage where there was something not blue shown up. And so that a person who's reviewing and searching this can let the computer search through hours and hours of footage and just pull up those few images where there was something that wasn't blue. And they look at that and go, yeah, that was a whale, or no, yeah, that is a piece of airplane, or something like that. So that's how, large data is manipulated in this way. The dark side of spreadsheets. Do. I wanted some ominous music here, but video production is not my thing. The European Spreadsheet Risks Interest Group, and that is a real thing. Imagine working for them. The European Spreadsheet Risks Interest Group has estimated that a whopping 90% of spreadsheets that have calculations in them have errors. And 50% of spreadsheets used operationally by large businesses have material defects. Wow. And they surveyed businesses and they found that 50% of executives have experienced problems from spreadsheets, including And all this list is true. It's in the USprig website, including staff dismissal, where staff performance was recorded in a spreadsheet. And because a spreadsheet showed that a staff had been performing badly, they were let go. And only after that was an error found in the spreadsheet. It's caused bankruptcy. In March 2018, an arithmetic error in a spreadsheet of a British drinks company amounting to £5.2 million led to its bankruptcy. In elections, in Malaysia, in the Malaysian election 2016, the spreadsheet tallying votes was listing all the votes and the candidates, and somebody noticed that the candidates 31 through 38 all had exactly the same number of votes as candidates 61 through 68. Oh dear. It's caused data leakage. Boeing put personal information of employees in a spreadsheet and then hid the rows, and then somebody else took that spreadsheet and emailed it out to a public entity. MI5, the British spy agency, once bugged 1,061 wrong telephone numbers because of a spreadsheet formatting error. Actually, it was a rounding error in the spreadsheet, which rounded off phone numbers as if they were numbers. And so all these wrong phone numbers were bugged. It's even affected scientists. Gene names in scientific literature. Genes are sometimes named things like APR1 or NOV2, and from literature that's been entered into spreadsheets for formatting, and then Excel converts them into dates. I'll show you how that works. Here's what happened in that genetic scientific research. Some of the gene names have names like March 5. And so I type them in here, I go March 5, and you see what happened there. It just changed it from March 5 to MAR05, and it's not saved as some text. It's saved actually as the 1st of March 2005 for some reason. If I another gene was called NOV7. NOV7 again, it changes it into a date, and this data was copied from some text, put into a spreadsheet, and then saved and processed and published without anybody noticing that these names are gone, and actual real data was lost this way. In a similar way, if you put in numbers in a hexadecimal format, then Excel will change it to something else and it loses it. So you have to be very careful with formatting. And these are some of the errors that have plagued spreadsheets over the years. So, what is the world coming to? With all these problems, you might think that spreadsheets are the curse of the modern world. But boy, have I got news for you. No, they are not. Spreadsheets are the curse of the ancient world as well. This is the Plimpton spreadsheet, which is cuneiform in clay tablet, and it dates back to 1800 BC, and this is the earliest known mistake in the spreadsheet. Now, I don't know how to decode that, but these are tallies of things which are added up, and an archaeologist added them up, and they added up wrong. Anyway, let's leave spreadsheet problems behind us, and I want to just talk through a few more ideas from the Think Maths website. One of the good things is spreadsheets for teaching circle geometry, the parametric heart shape, and I've downloaded that one here and I'll show it to you now. This is a love heart, mathematical. There's the equation. X, so this is a graph in the x-axis and the y-axis. X equals a sine cubed b theta, and y equals c cos d theta minus e cos f theta minus g cos h theta. And you get to play with these numbers here. And down here are all the 100 points around that. So what happens, you can take your students, let them play with this. What happens if you make that a 2? The heart gets wider. Okay, what happens if you make this a 2? You get all sorts of interesting shapes. And you can let them play with that and see what each of these factors does. See how it manipulates the shape. Some of those seem more powerful than others. And you can see we're getting into something that's quite different now. You can get all sorts of shapes, so let them play with that for a bit. Perhaps the simpler one is the cardoid, which is about circle geometry. And again, we've got this formula R equals A minus B sine C theta. And the values are here, A, B, and C. And so you can get your students to play with those values. If you put in 0 for B, okay, you immediately get a perfect circle. And what I've done here, when you download the spreadsheet, this column here is not, whoops. This column here is not there. So what I've done is that here's the angle in radians. And what I've actually done is turn that into degrees. So here I've written a formula. And this one is equal degrees, and then open brackets B14, which is that cell right next to it. And then copy that down all the way down to the bottom to 360. And that is 100 points around the circle. Each of those dots is 3.6 degrees. And that maps the perfect circle, and there are the X, Y coordinates of each one. So you come down to 90 degrees, and you can see that we've got 1 in the Y and 0, almost 0 in the X-axis. And so if you have a look here at this formula here, this formula is C14, which is this value here, the radius, times cosine of that angle. That's the X coordinate. And the Y coordinate, of course, is the sine of that angle. So you're teaching geometry and polar geometry about how all those points are made, sine and cosine. Then if we put 1 back in here and we go 0 there, again, we get the circle because there's no angle there. But now we start playing with these numbers. What happens if we put 2 in there? We get this sort of shape. If we put 3 in there, then we get a 3-leaf clover. If we put 4, we get a 4-leaf clover. And then what happens if you start playing with this number here? You can get the students to say how this works. And so we then have a double 4-leaf clover. And so by allowing the students to just manipulate his and play with these numbers, you can see they can learn sort of how all these things actually fit together and get a really good feeling for what is this X coordinate, this cosine of that number. What does that mean? What does the Y coordinate mean when you got the sine of that number? So a good way to teach polar geometry there. For younger kids, this site has wrapping presents with maths. And they've got a video there and some things about how to wrap presents mathematically and cutting the paper just the right size and just the right shape so you get the folds ending up in exactly the right place. It's quite a neat trick. The next one down is Euler's formula, which is actually a puzzle. And the puzzle consists of the instructions on the website. The puzzle says you have 3 houses and you have 3 utilities, water, electricity, and sewage. And you have to join a line from each utility to each house without any of the lines crossing. And it's a puzzle that is impossible to do on a flat sheet of paper. And yet it is possible if you do it on an ordinary coffee mug, as long as the coffee mug is a handle. And so you can work through then what is planar maths and graphs and what is it about the mug that allows this puzzle to be solved. If you're the sort of person who hates paper and you hate trees, you can download and print 1.60934 kilometers of pi. And what Matt's done is on an A4 piece of paper, he's done digits about 4 centimeters high, and that's pi to, I've forgotten how many thousand spaces, that's how many thousand digits. But you can do that and wrap it around the school, around the classroom, and there's also ways for going around corners, that kind of thing. There's instructions on how to make a dodecahedron out of A4 paper as well. There's lots of things to do. And this is the website here, thinkmaths.co.uk resources. And like I say, there's lots of things to do. Each of them have instructions given, instructions to the teacher. Some of them have printable things. Some of them have further learning to do with students. So there's lots of, these are ones that are focused on maths, of course, especially. But there's lots of maths ideas. There's a few science activities there. So I commend thinkmaths.co.uk. And that, of course, again, is put together by Matt Parker and his team, who are three British, Matt Parker and his 2 teammates are 3 British, not comedians, mathematicians, although they are fairly funny as well on their YouTube page. Thank you for watching. I hope this session has been useful to you and helps just a little bit. I'm happy to say that most of the things we talked about can be done online, so for distance learning with students. If this has been helpful and you want to find out more, feel free to email me please, pthew@csu.edu.au. Thanks for your time.